Hello, everybody. In this video, we're going to talk about vector functions and derivatives. In the past, you've worked a lot with functions which take a single real number as input and a single real number as output. So functions of the form f of x equals y. We've also done a lot of work with vectors. Typically, vectors with 2 or 3 components. So here Rn is usually R2 or R3. And we'll often write the vector v as either a row vector. So for example, v1 up through vn, or you might write it as a column vector, v1 down to vn. And today, we're going to start off by talking about vector-valued functions. Typically, we'll write these in the form f goes from r to rn. Specifically, they're going to have one real number input and usually some kind of a vector as output, either a 2-component vector or a 3-component vector. And to avoid confusion and indicate that I am getting a vector as output, I'll often write the function with a vector symbol above the letter indicating the function. One such example we've seen in the past would be the equation or the function, say function to be more specific, whose graph is a line in 2 or 3-dimensional space. So for example, we've written this in the past as L of t is equal to some slope vector. I like to think of this as a slope vector, m times t, plus some point on the line. And to be consistent with our new notation, I'll write this function L with a vector above it. So for example, we might have an equation of the form L of t is equal to, 1, 2, 3 times the vector t plus 3, 3, 7. And for every value of t, you have a point on this line. There's other equations that we've looked at as well, other functions. And so a parametric form for the equation of a circle. So a function that parameterizing a circle would be the function, I'll call that c of t, is equal to cosine t, comma sine t. Right, in the xy plane, that traces out a unit circle. The graph of this function, like so. To go all the way around, we'd want t to go at least from 0 to 2 pi. And there's other very interesting functions of this form out there as well. One more example, one which I'm a big fan of, is the function k of t is equal to t cubed minus 3t, comma, t to the 4th minus 4t squared. Right, to graph an equation like this, you could, for example, set up a table and figure out for each value of t, what are some points, the x and y coordinates of some points. But I'll just show you what the graph looks like. You can graph a few points on this, but the graph overall actually looks like a trefoil knot. And so in particular, I could label some points on this graph. And so this is the point where t equals -2. I think somewhere around here-ish is t equals -1. Keep traveling around the curve. T equals 0. When you plug 0 in for t, you're right at the origin. Then the curve is very symmetric over here as t equals 1. Keep traveling around to t equals 2. It's a very interesting equation. All right, now one thing that we know is that You can do a lot of things with vectors. Right, so we have some basic operations on vectors. For example, if we have two vectors, let's say v is equal to the vector v1 comma v2, w is equal to the vector w1 comma w2, we've learned that adding those two vectors together means that we're adding them component by component. So v plus w would be the vector v1 comma w1, v1 plus w1 comma v2 plus w2. Or if we're to multiply a vector times a constant, that would be that constant times v1, the constant times v2. These operations also apply to functions as well. For instance, if I have a function, a vector function f of t, and I'll do the two-dimensional case. So this vector function, each component of my vector, we can think of that as a function. For example, when we were looking at the equation of a knot before, right? The equation of a knot, that's why I used k. Think of that as a function in the first component and a function in the second component. So I might want to write that as k1 of t, comma k2 of t. So the idea is these operations also apply to vectors. For example, if I have two vector functions, so f of t is equal to f1 of t, comma f2 of t, and vector function g is equal to g1 of t, comma g2 of t, then we can also add together vector functions. And so I could say f plus g applied to t would be equal to f1 of t plus f2, or plus g1 of t, comma f2 of t plus g2 of t. Similarly, you could multiply a vector function times a constant. So if I have c times f applied to an input t, that would simply be c times f1 of t, comma c times f2 of t. And of course, similar statements hold for vector functions with three components in three-dimensional space, or really any number of components overall. Now, for our purposes, we're going to be interested in doing some basic calculus with these vector functions. So we can define a limit as t goes to some constant, let's say a, of a vector function f of t. And we'll define that to be limit as t goes to a of f1 of t, comma, the limit as t goes to a of f2 of t. Because limits apply to vector functions in this way, it makes sense to define the derivative of a vector function. So the derivative of vector function f of t, which we might write in one of two ways. We might write using the prime notation, so vector f prime of t, or we might also have occasion to write df dt, or even d dt of vector f. There's one way which makes sense to define it. Right? If there's any justice in the world, we should be able to make sense out of the definition f prime of t is equal to the limit as h goes to 0 of the quantity f prime of t plus h minus, sorry, not f prime of t plus h, that's what we're defining. F of t plus h minus f of t all divided by h. And it makes sense to subtract two vectors. This operation is well defined. Then dividing them by the constant h, that's the same as multiplying by 1 over h, and then taking the limit of that. Those are all well-defined operations. And we'll see that this must, in fact, equal f1 prime of t, comma, f2 prime of t. Right? The derivative of a vector-valued function is just the derivative of the individual components, as you might expect. So we should do a few examples, of course. Okay, so for example, the trefoil knot equation from before, that was the function t cubed minus 3t, comma, t to the fourth minus 4t squared. To calculate the derivative of that, vector k prime of t, it'll be 3t squared minus 3, comma, 4t cubed minus 8t. Just like the derivatives you learned about in Calculus 1, but multiple times the fun because we get to calculate just more than one derivative. Here's another example. Let's not do k this time. Let's do c of t, the parametric equation for a circle. That's cosine of t, comma, sine of t. We calculate the derivative of that. The derivative of cosine is negative sine of t. Derivative of sine is cosine of t. All right. And finally, what if we have something like the equation of a line? And so, for example, we often wrote this as something like 1, 2, 3 times t plus 3, 3, 7. And if it helps, you can condense this into a single function, t plus 3, 2t plus 3, and 3t plus 7. Then calculate the derivative of this function. You'll find that what you're left with is actually 1, 2, 3. Because we have linear functions, each one of these positions, constants drop out, and we're left with the coefficients of t, which are 1, 2, and 3. It's as if a vector of constants behaves like a constant. Right? L of t looks like a constant vector times t plus a constant. The derivative of a constant times a variable is that constant, and the derivative of a constant is 0, so that drops out. So those are some examples of calculating derivatives. At some point, I'm sure we'll have occasion to talk about things like equations of tangent lines. But before we do that, we should establish some of the basic differentiation rules. So differentiation rules. Right, some of the rules you know from standard calculus automatically apply because of the way that vector addition and scalar multiplication work. So for example, throughout all of these, let's say f of t is still the two-dimensional vector with component functions f1 of t and f2 of t. Let's say that g of t is again the vector function with components g1 of t, g2 of t. And if we want to do the derivative of a sum of functions, and because of the way vector addition works, this is, as you might expect, df dt plus dg dt. Or similarly, if you have a constant times a function, so if we have to calculate the derivative of a constant times a function, again, because of the way the scalar multiplication works, this is a constant times the derivative of the function. But there are some particular circumstances for vector functions which are a little bit different, which we should discuss now. So for example, let's say we'll let p be just a regular function from R to R. And let's say we want to calculate the derivative of the function p times the function f. Right? Is that going to be like a product rule, or is that going to be like a constant multiple rule? And so the question is, if we want to calculate the derivative, say of p of t times f of t, what will that equal? Well, when in doubt, we'll actually multiply everything out. Right, so this is equal to p of t times the vector function f1 of t, comma, f2 of t. And the way scalar multiplication works, this is equal to p of t times f1 of t, comma, p of t times f2 of t. I should say what I'm calculating here is first, I'm not doing the derivative yet. This is all p of t times the vector function f of t. So now if we want to do the derivative of p of t times vector f of t, then we're doing the derivative of this expression on the right, and sure enough, that's going to turn into a product rule. And so the derivative of p of t times vector f of t is equal to the derivative of this expression, p of t times f1 of t, comma, p of t times f2 of t. And because of the way derivatives work, we're going to calculate out the derivative of each component one by one. And so this is equal to the derivative of a product of functions. And so the derivative of p, I'll write this a little bit more succinctly, derivative of p times f1, comma, the derivative of p times f2. And since those are both functions, the product rule from single variable calculus applies here. Going on to the next page, this is going to be equal to, see, we'll have p prime of t times f1 of t plus p of t times f1 prime of t. For the first component, it's a product rule. And the second component, also similar, that's going to be p1 of t times f2 of t plus p of t times f2 prime of t. Now, if you want, there's also a way to probably simplify this a little bit. We could rewrite this as p prime of t times f1 of t, f2 of t, plus p of t times f1 prime of t, f2 prime of t. Because what I'm doing here is I'm factoring out p prime from f1 and f2, right, in the first and second components, and then I'm factoring out just p of t from f prime 1 and f1 prime and f2 prime, the second components. I could also rewrite this as p prime of t times vector f of t plus p of t times vector f prime of t. And so this is what we get when we're trying to calculate the derivative. Maybe I'll use the prime notation for consistency. We have p of t times f of t prime. And so this is one of our multivariable vector function calculus differentiation rules. And so there we have a product rule, but there's other rules you might remember from calculus. So for example, what about the chain rule? Right, so again, let's say that p is a function from R to R, one input, one output, and vector f is a function from R to R2, which we will write as vector f with component functions f1 and f2. So in this case, it makes sense to talk about the following composition of functions. So let's say we have f of p of t. In this case, you have your input, and you have a single input, the value t. Its output through the function p is again a single real number, which you can then use as input for the vector function f. Right, so this composition of functions would give you f1 of p of t, comma, f2 of p of t. Of course, the question is, what's the derivative of a composition of functions like this when one of them is a vector function? So what is f of p of t? Let's calculate the derivative of the entire expression. Well, in that case, we're calculating the derivative of f1 of p of t, and then the derivative of f2 of p of t. So the derivative applies to both components, and we're back in kind of the realm of ordinary single variable calculus, and we know that the chain rule applies in this situation. So I could simplify this as f1 prime of p of t times the derivative of the inside function, which is p of t, comma, f2 prime of p of t times the derivative of the inside, which is again p of t. And if we want, we could actually simplify this again. We can factor some things out. So both components are being multiplied by p prime of t. So we could factor that out. Left with p prime of t equals, we'll have this component here, f1 prime times p of t, and f2 prime of p of t. We could actually write that very nicely as f of p of t. And this is the chain rule, but in the context of vector functions. Right, so we have another useful rule. Right, it kind of agrees with what we might expect from our previous experience. Definitely another rule to keep in mind. Now, one more rule that might be worth talking about. There's lots of different rules, but we have something in vector calculus or in our study of vectors that doesn't necessarily correspond to something we've seen before. We have dot products of vectors, and we even have cross products of vectors. What I'm really interested in is the dot product of two vectors. So the final question I'd like to consider is, what is the derivative of the dot product of two vector functions? So again, f and g, for simplicity, I'll assume that, again, vector f has components f1 and f2, and vector function g has components g1 and g2. And of course, this also applies for vectors of three or more functions, or three or more components. So if we don't know what the answer is, it's best to expand it out. So let's go ahead and do that. So I have f of t dot product with g. And so first, before applying the derivative, we'll calculate the dot product, and we'll have, when we do the dot product, it's not really a vector anymore. We have f1. I'm dropping the of t notation just to make this a little bit more reasonable. So I have f1 times g1 plus f2 times g2. Those are all functions, remember. I'd like to calculate their derivatives. Now we know that the derivative of a sum is the sum of the derivatives. So the first step is we could break this up into two smaller problems. f1 times g1 prime plus f2 times g2 prime. Now each one of these is just ordinary functions, and we have to use the product rule for each one of these expressions. So by the product rule, the first term becomes f1 prime times g1 plus f1 times g1 prime. The second part with the f2's, again, is a product. So when we calculate its derivative, here we'll have f2 prime times g2 plus f2 times g2 prime. And it looks like a lot to remember, but we can actually make our life a little bit easier if we rearrange and regroup these terms. So for example, the two that I'm underlining now, I could rewrite that as f1 prime comma f2 prime dot product with g1 and g2. So I'm trying to gather together terms with like derivatives. Plus, it's these other two terms, the ones with the derivatives of g in them. I could rewrite that expression as the vector f1 comma f2 dot product with g1 prime comma g2 prime. Right? And each one of these, the first one is the derivative of the vector function f. So I could write this as vector f prime dot product with, let's say I've got the vector whose components are g's. So vector f prime plus g, or dot g, plus, and over here in blue, I've got the vector f function dot product with vector g prime. Right, so it looks like a product rule. In fact, it's a product rule for dot products of vector functions. So again, a useful thing to remember and add to our sheets. As always, it's definitely worth taking the time to practice. So, for example, here's something you can try out on your own. Let's say I have two functions. Let's say f of t is going to be the function, let's say t, let's say not just t, let's try 2t plus 3 comma t squared. Let's say g of t is equal to, let's make this one 5t to the fourth comma, let's say maybe t squared plus 1. Just as an example of that dot product rule, it might be worthwhile to check that if you do f dot g prime, check that that actually works out with this dot product definition. Right? You have two different ways to calculate this. Plus, see, f dot g prime. And so check this fact by calculating in two ways. First, on the left-hand side, calculate the dot product of these two functions first. Maybe I'll just get you started here. F dot g is equal to, let's see, I have f1 times g1 plus f2 times g2. All right, so this function is, see if we expand this out, we'll get 10t to the fifth plus 15t to the fourth plus another t to the fourth plus t squared. And so we could simplify this to 10t to the fifth plus 16t to the fourth plus t squared. Right, so that should be the dot product of f and g. So on the left-hand side here, you could try calculating the derivative of the dot product, calculate the derivative of this function. And if math is consistent, if math works, then you should get the same result if you calculate over here on the right-hand side. In other words, figure out f prime, right? So find the derivative of this vector function and do the dot product of that with g. For the second set of parentheses, find the derivative of the g function, do the dot product of that with f, and then try adding all those things together. And hopefully you will get the same thing you find when you calculate the derivative of the dot product of f and g. Remember, you learn math by doing math. Good luck.